Hello everybody, Mr. Gomez here, and today we're going to be talking about some of the most foundational aspects of doing science quantitatively, doing science with numbers. Those are dimensions, units, conversions, and measurements. So, let's begin by defining a dimension. A dimension is a physical quantity that you can measure. What are some common examples of dimensions, you might ask? Well, we have mass, time, distance. Those are all things that we can measure. Mass being abbreviated, of course, m. Time being abbreviated with the lowercase t. Distance being abbreviated d. So then what is a unit? Well, a unit is a way of measuring a dimension. So we'll give you some examples here too. For the dimension of mass, I can measure mass in grams, kilograms, pounds. For the dimension of time, I can measure time in hours, seconds, days, years. And for the dimension of distance, well, I can measure distance in feet, miles, kilometers, centimeters. A good way to determine if something is a dimension or a unit is try putting a number in front of it. For example, I wouldn't say I am 6 distance tall. I would say I am 6 feet tall. And so units are often associated with numbers right before them, and therefore we just kind of hear that as more natural. If it's a unit, it'll have a number come before it. Lastly, we have these things called compound dimensions and units. So, what are compound dimensions and units? They're dimensions or units that are combined through mathematical operations. An example of this might be density. We express density, calculate density, as mass per volume. So here we have two dimensions, mass and volume, being combined through a mathematical operation, this operation being division. this all leads to a compound dimension, this dimension being density. It's important to note here that we often express equations in terms of dimensions and not units. But whatever units we put into the equation are the units we get out. For example, if I put grams in for my mass and milliliters in for my volume, then my compound unit I get out for my density would be grams per milliliter. No big surprises there. Moving on. And so now we need to talk about the metric system. And what the metric system is a way of making new units using base units and prefixes. So the idea works like this. A prefix listed here in this far left column. And so I know this might be hard to see on the video, so it's important that you have this image with you while you're watching this. A prefix plus a base unit will equal a new unit. So what are some base units of the metric system, you might ask? Well, first of all, on this figure, base units go in right here. And some of the most common base units would be meters, a unit to measure the dimension of length, grams, grams measure the dimension of mass, liters, liters measure the dimension of volume, and seconds, seconds measure time, of course. So how might this work? Well, if we have just the base unit, then this figure is telling us we have one of that. But if I wanted to make a new unit by adding a prefix to it, then that new unit, for example, a kilometer, would be 1,000 of the base unit. So, in example, 1 kilometer equals 1,000 meters. This way of changing units by powers of 10 is extremely systematic and useful when it comes to quantitative science. So over here you can see that we have the scientific notations, which we'll talk about in just a second. But another way of writing this would be 1 kilometer equals 1 times 10 to the third meters. So I can take the prefix kilo, and I can replace it with the scientific notation listed here, 10 to the third. So I take kilo, I replace it with times 10 to the third, and I'm back into the base units, and this can be done interchangeably. So on this diagram, if I move up above the base unit section, I'm making things bigger. I'm creating units that are bigger than the base unit. And if I move down below, you'll see the scientific notations have negative exponents, and that means I'm making units that are smaller than the base unit. So we got a little taste of scientific notation in the last slide. But what is scientific notation? Well, scientific notation is a way to express really large or really small numbers easily. Remember, scientists are lazy. So here we can see the basic form of scientific notation. It always takes this form. Some number, here we call that number A. And A must be between 1 and 10 for this to be true scientific notation. So it's a number between 1 and 10. It can have a decimal point, of course. It doesn't have to be an integer, but it must be between 1 and 10. And then we always take that number and we multiply it by 10 raised to some power. Okay, so let's see how this would look. For example, 2.3 times 10 raised to the third power is a scientific notation of writing a number that is, well, let's expand the power first. 2.3 times 1,000, 10 to the third being 1,000, and then we have just a multiplication problem. 2,300. I had to think about it for a second there. So, it's helpful sometimes to expand the power, but how it's often taught is that you just move the decimal point. Because every time I multiply by 10, whether it's 10 in the numerator or 1 over 10, dividing by 10, I'm just moving a decimal point, and I'm moving it to the right if I'm multiplying by 10, or moving it to the left if I'm multiplying by 1 over 10, or dividing by 10. So, the easiest trick for scientific notation is to recognize a number, recognize the power on 10, in this case it's 9, and move the decimal point 9 spots to the right. Now, had 9 been a negative number, we would have moved the decimal point 9 spots to the left. So we'll quickly see how that looks. Let's say I take 4.4 times 10 to the negative fourth. So here I recognize I have a negative exponent, and so I need to move the decimal point not to the right, making the number bigger, but I need to move it to the left, making it smaller. So this equals 4.4 times 1 over 10 to the fourth. And so that's where that dividing by powers of 10 comes in, which is the same as saying 4.4 times 1 over 10,000, which in essence, and you can skip these mathy steps in between, is the same as just moving this decimal point 4 digit places or spots to the left. So that would be 0.00044. Right? And so I just took this decimal point and I moved it over 1, 2, 3, and a fourth. I ran out of room, but to get here at this final number. So this brings us to one of the most important parts of quantitative chemistry, and that's converting dimensions and units through a process called dimensional analysis. I think it's best understood through seeing an example. So on the left, I'm going to work through writing out the procedural steps of dimensional analysis, while on the right, I'm going to answer the question, if I am 67 inches tall, how many centimeters am I? So here we have the procedure. Here we have the example. So the first thing I want to do is identify what the desired unit is. What unit will my answer be in? So here, the desired unit is centimeters. I know that once I get an answer in centimeters, then I'm done. And so I always write the desired unit to start out, and I put that next to an equal sign. I'm building the problem right now. And so I know I want to get some number which will go right here. I don't know that number yet. Centimeters equals, and then I've got to build the equation, or the expression rather, on the right side that will tell me how many centimeters. So the next step is I got to find what the question gives me to start with, the given. I want to find the given number and unit, because I have to convert a number into a different number with a different unit. So there's always a number and a unit. in this question, the given number and unit is 67 inches. So, I take what I started with up here in step 1. I'm still looking for some number of centimeters. And I'm going to say that equals 67 inches. Okay, so I want to find what number of centimeters equals 67 inches. Pretty straightforward enough. But I need a conversion factor so that I can find this number. I'm going to write this in red to keep this color scheme going. So I've got to find the required conversion factor. You've got to find the required conversion factor. Sometimes the question will give you these. Sometimes they're taken to be common knowledge. And sometimes you got to go look them up in a book. So I need a conversion factor that gets me from centimeters to inches or inches to centimeters. And so I just happen to know that 1 inch equals 2.54 centimeters. Okay, so this is written as an equality. 1 inch equals 2.54 centimeters. But to complete this problem, I need to rewrite my equality as a ratio, as a division problem. So I could say there's 1 inch per, we read the division sign as per 2.54 centimeters. I could just as easily say that there's 2.54 centimeters per 1 inch. So you can flip the conversion factor just so long as when you flip the units, you're flipping the numbers with it. Right? So all three of these are true statements. Now I've got to string it together so that I'm canceling out my given unit and I'm getting into my desired unit. And I'll show you how that works. So string it together to cancel out the given and get into the desired. So I know up here, I'm looking for some number of centimeters that's equal to 67 inches. Well, I'm going to just rewrite that for right now. Looking for some number of centimeters equal to 67 inches. And now I can use one of my conversion factors to cancel inches and get into centimeters. One of these is the right choice and one is the wrong choice. And I will say right now that this conversion factor is the right choice. Why? Let's see. So I'm going to multiply 67 inches by this conversion factor. 2.54 centimeters per 1 inch. Why was that the right choice? Because inches divided by inches cancels out. Just like 3 over 3 cancels out, or A over A cancels out. And now I'm left in the unit of centimeters, which just happens to be my desired unit. So I only have to do the math now, but I want to reinforce the idea that this whole concept of dimensional analysis works on the mathematical principle that A times B over A equals B. So A is my given, B is my desired. I've got to cancel out my given using some conversion factor that relates A to B. So it really looks like A, my given, times B over A, a conversion factor, equals B. Right? We can all see that as mathematically true. So I said, lastly, you got to do the math. And how would the math like this look on the calculator? So step 5, do the math. So once I've determined that my units cancel out correctly and I go from the given inches to the desired centimeters, I can pretty much disregard the units because I can't put them in a calculator. I can't do the mathematical operations with letters in there. And I can just say that 67 times 2.54 over 1 equals some amount of centimeters. So I'm going to just take this whole thing, multiply my numerators, and divide by my denominator. Mathematically, that looks like some number of centimeters equals 67 times 2.54 all over 1. We know anything multiplied or divided by 1 is itself, so really I could forget about that 1. Go to the calculator, 67 times 2.54 equals 170.18. So the answer to this dimensional analysis question, my height expressed in centimeters, is 170.18. So you might have found that last dimensional analysis problem to be a little trivial. So I'll show you a more complicated dimensional analysis problem that solves a real-life example. Mr. Gomez drives 23 miles per day, gets 28.6 miles per gallon, and gas costs $1.98 per gallon. How many dollars do I spend on gas in 5 days? You might want to know this. So I've got to run through the procedural steps again. First, what is my desired unit? Well, my desired unit is dollars. I want to find out how much money I'm spending. So I'm going to write dollars as my unit, and keep in mind that I want to find out how many dollars, right? How many dollars. And then I've got to find the given unit. So in this case, I see a lot of numbers up there. I do. And it can get a little confusing when you see a lot of numbers, but I will tell you that the given unit is 5 days. So why is the given unit 5 days? Because that's just how this question is written. I could equally have written a question, how many dollars do I spend on gas in 10 days? Or how many dollars do I spend on gas in 12 days? But I chose 5 days for this question, and that brings up the important point that the given unit is usually unique to the question, whereas all conversion factors should be true regardless of what the question's asking about. So again, I'm going through the steps. I want to know how many dollars is equal to 5 days. And now I've got to find some conversion factors, and this one will have more than just one, like the last one, that will get me from days to dollars. Okay, so I'm going to go back, I'm going to look in the question for those conversion factors. I see that I have 23 miles per day. I have 28.6 miles per gallon. And gas costs $1.98 per gallon. All of those include the word per. And that word is telling me that those are conversion factors. They let me convert between units. And even in this case, between dimensions. So, here's my setup. But before I can do this problem, I'm just going to write out my conversion factors so that I can easily use them in this problem. So, 23 miles per day expressed as a ratio looks like this. Keeping my color scheme going. Right, so I interpret 23 miles per day as 23 miles per 1 day. It's important to put that 1 in there. 28.6 miles per gallon, I interpret that as 28.6 miles per gallon, 1 gallon. Again, keeping that 1 in the denominator is very important. And then lastly, $1.98 per gallon, written as $1.98 per 1 gallon. So, I must string together these conversion factors so that I can cancel out days and get into dollars. And this one, like I said, is not going to be a one-stepper, so let's see how it goes. First thing I'm going to do is I'm going to ask myself, what do I know about days? I've got to cancel days. Well, I know that for every 1 day, I drive 23 miles. Okay? So I know that the numerator, and you could think of this as 5 days over a unitless 1, right? The numerator, the unit on the numerator must be the unit on the successive denominator. Right? So whatever's up here must go down there. And now I know that days cancel out days, and I said, what do I know about days? Well, I know for every 1 day I drive 23 miles. So my unit in the numerator is going to be miles. Once my units are set, then I can plug in the numbers. So 1 day is 23 miles, right? I just took this conversion factor and I wrote it in. Now I've got to ask myself, what do I know about miles? I know that for every 28.6 miles, I'm going to burn up 1 gallon of gas. But miles is in the numerator here, so therefore miles must be in the denominator on this next conversion factor. So I write miles in on the denominator, and then I have a conversion factor that relates it to gallons. But since I flipped the units to go from this to this, right? I flipped miles and gallons, I must also flip the numbers. Right? So for every 1 gallon, I drive 28.6 miles. Now I just see that miles cancels out, and my units are in gallons. But what do I know about gallons? Now I know that for every 1 gallon, I'm going to pay $1.98. And I know that gallons is in the numerator here, so I want gallons in the denominator there. And I want to get to dollars, right? Some amount of dollars. And here I'm getting a little unconventional because I'm writing the dollar sign on the wrong side, but bear with me. So I know that for every 1 gallon, and I can see that my units of gallons have now canceled out, I'm going to pay $1.98. Lastly, I can see that my desired unit is dollars, right? I want to get into dollars, and through all this cancellation, days cancel with days, miles cancel with miles, gallons cancel with gallons, I'm left in dollars. So the last step I have to do is just do the math. How would this look on a calculator? I've checked my units, they all work out, but I want to know how would this look on a calculator. So I'm going to take all my numerators, 5 times 23 times 1 times $1.98, and I'm going to divide them by all of my denominators multiplied together. So I've got 1 day, times 28.6 times this last 1. So here, since I knew all of my units worked out, I can just kind of forget about the units and just get an expression of numbers. There's lots of ways to reduce this fraction. I will say that be careful to make sure that all of these numbers being multiplied together are in the denominator, especially if you're using a TI graphing calculator. So I get 7.96. I spend $7.96 every 5 days on gasoline, given this information. I want you to also know that since anything times or anything divided by 1 is itself, you could just do this math without the 1s. I can forget about all those 1s that often show up in conversion factors, and I can just say that 5 times 23 times $1.98 over the 28.6 equals, and I would get the same answer, the $7.96. Perfect. The last two things I'd like to talk to you about are two properties of experiments, precision versus accuracy, rather properties of data even. So these are two words that we use pretty synonymously in our everyday speech. It was precise, it was accurate, but in science they mean two very different things. So, like I said, these are properties of experiments or properties of data sets. So, precision is the property of an experiment to produce consistent data. Accuracy, on the other hand, is the property of an experiment to produce data close to the true value. So we can often think of these two properties of experiments as where you fall on the bullseye. So to be precise but not accurate is to miss the bullseye but to miss it consistently. So you have a tight grouping but you're not close to the true value. So you can get consistent data but it's just not right. To be accurate but not precise is to be around the bullseye, but you're inconsistently around the bullseye. So you're a little scattered, but you're close to the center. To be not precise nor accurate is to be pretty much all over the map. You're not getting data close to the true value, nor are you doing it consistently. The best experiment would be the experiment that is both precise and accurate. So you are consistently getting the bullseye. You're consistently getting the right values. So these are important ways of talking about experiments and thinking about experiments, especially as we start to design our own experiments.